Right. So the final talk of the morning will begin by Rahul, causal inference with corrupted data.
Thanks. This is a joint project with Anish. Anish, would you like to wave? We're both fellows here at Simons for the semester in causal inference. Anish is also a postdoc at UC Berkeley, and I'm a PhD at MIT. The motivation for this project is the 2020 US Census. The United States Census is a very important data set. It's high dimensional. It's actually required by the US Constitution that they provide this, and it's ubiquitous in social science and policy making. Decisions made by the Fed, by the Department of Labor, and the Council of Economic Advisors, for example, are based on data published by the Bureau. Some slowly breaking news is starting with this census, it'll be published with differential privacy. And I'd like to read an excerpt from the census website. They say, "We're deploying differential privacy, the gold standard for privacy protection in computer science and cryptography, to preserve confidentiality in the 2020 census and beyond. There are many variants of differential privacy. The one selected for the 2020 census introduces controlled noise into the data in a manner that preserves the accuracy at higher levels of geography." And this is worrisome for people who use the census and census data to inform policy, to do causal inference. And in fact, in the statistics literature, there's a warning that there will be a painful trade-off between privacy and precision. And in the economics literature, there is, even from About, who is the chief scientist of the census, a warning that this is a painful trade-off we have to make. Now, why does the census need privacy? To the credit of the US Census Bureau, they actually simulated an attack in the 2010 census. So they took different commercial data sets, and these commercial data sets have, let's say, names and addresses, and then they tried to use that to merge it with census data and see what's revealed. In particular, what did they find? They said that our simulated attack demonstrated that, depending on the quality of the external data used, between 52 and 175 million respondents in the 2010 census can be correctly re-identified from the reconstructed microdata. And this had big shockwaves, and immediately they kind of pivoted the policy of how they're going to be publishing data in 20 census and hereafter. Another recent announcement related to this privacy protection issue is that they're going to discretize certain variables that they release, such as wages. Now, wages are really important for economists, and some have already documented what this might do. So there is something called the Atlanta Fed Wage Tracker. The Fed is part of the Federal Reserve System, and they track wages over time. They have these plots of wage growth that people use to inform policy. You can see the original data series before thinking about how discretization will be implemented, and it's this kind of blue/green series. But if you implement the discretization they've proposed, you get this red series. So you can see it's very corrupted, and this is very worrisome. There was a big backlash, and actually the Census Bureau announced that they will delay this policy until maybe inflation abates or something like that. So what does this mean for causal inference? Social scientists are worried about these new types of data corruption. Of course, to people here at Simons, these might not sound new, like differential privacy and discretization. But even before the 2020 census, these data sets had kind of old or classical types of data corruption, which are very much studied in causal inference, such as missing values and measurement error. Now, what's the standard practice? What's the standard workflow for, let's say, an economist trying to measure a treatment effect from one of these data sets? Well, they'll do some data cleaning, and then they'll do some data analysis that kind of ignores the bias and variance consequences of the data cleaning. In particular, what are those consequences, roughly speaking? Well, when you clean a data set, you tend to make it more homogeneous and correlated than it originally was. And in the effort to rein in the bias from different types of data corruption, you've probably also really depleted the variance. Existing confidence intervals ignore this phenomenon, and in simulations, you can show that typically they'll be too small, too optimistic. Coverage will be about 70% instead of the 95% you'd expect. So what's the kind of solution that we would like? Well, we would ideally have a solution that estimates causal parameters as if the data were uncorrupted, yet still adjusts for data cleaning in the confidence interval. We want this procedure to not require knowledge of the corruption covariance structure as well. If such a procedure existed, it would in some sense preempt this looming trade-off between privacy and protection, privacy and precision that is faced by social scientists and other researchers who use these data sets. This is maybe the most important slide. Why is this hard? I think that several challenges arise, and here are just a few of them. First of all, when we justify confidence intervals, we typically appeal to a central limit theorem that requires independence or at least weak dependence among observations. Meanwhile, data cleaning in general induces really strong dependence across observations, and even if you think about it, across every single entry. The next issue is that if we think of the data cleaning literature, perhaps we turn to the matrix completion literature, we see results that, if we want relatively good rates, are for recovering not matrix entries entry-wise or in max norm, but rather kind of matrix entries on averages across rows and columns, a Frobenius norm type of idea. And so I think a conceptual question is, how is this even related to causal inference? The third challenge happens to be about how fast are these rates we get from the matrix completion literature. And the best ones are going to be actually a little bit slower than n to the minus a half if rank is increasing. So how could we possibly get a standard error that is of order n to the minus a half? These are, I think, three difficult technical challenges that we are going to try to address. And here's what we propose in our project. We're going to propose an end-to-end procedure that includes data cleaning, estimation, and finally inference with a data cleaning adjusted confidence interval. Theoretically, we'll prove root n consistency, Gaussian approximation, and semi-parametric efficiency. Throughout, it's going to be finite sample arguments at each step. And our key assumption is that the true covariates are approximately low rank. In doing so, we try to overcome the trade-off between privacy and precision, where we think about privacy as being at the individual level and precision as being at the population level. If you believe our conditions, then indeed we have. I'd love to talk more. Here's my email address, and maybe I can take some questions.
Yeah, questions?
So, is it a CLT asymptotic argument, or is it some other kind of UQ?
It's going to be a Bayesian type argument at the end. So it's going to involve a kind of sample splitting, and we'll develop a new theory of implicit data cleaning that preserves independence across rows.
Yeah, triangular array kind of story.
Yeah, and I'd be happy to talk more.
That was the question that I had.
Oh, right. So maybe I'm not really, I don't know how Census 2020 is working, but what is the meaning of the phrase discretization? I mean, I thought that the data are discretized. We have every day, it's not any analog those terms. So what is the meaning of the discretization that I lost?
Good question. So wages are reported for example, this variable, what is your hourly wage? And that is continuous in the sense that it's up to the cent reported historically. The Census Bureau, which publishes many data sets, said that hereafter we're going to round it to the nearest 50 cents. And a lot of information is lost if you do that. One of the things we'll do in the paper is we'll propose, well, if you want to discretize, here's a way to discretize. It's not actually just rounding to the nearest 50 cents. It's kind of doing a discrete process that's centered at the truth. And if you do it this way, then you can still get the causal inference you want downstream.
I see.
Maybe just take an opportunity with this crowd that there's been a bit of a breakthrough both at Stanford and Emmanuel's Canvas's group at ours here on conformal prediction. Conformal inference. So you can get uncertainty distribution free, non-asymptotic, and you don't need independence. You need exchangeability. And I think a lot of what you're doing with this kind of thing and conformal is actually kind of, in fact, we have private prediction sets paper where we talk about doing this with conformal. So if you're, I think a lot of theoreticians would, if you haven't looked at the shed, you'll want to, because there's a lot of open theoretical questions about it. It's just it's not asymptotic, it's not CLT based, it's a whole different kind of more algorithmic way of thinking about it.
I see, yeah, thanks for the references. I'll definitely read into it.
Yeah, if anyone's interested, come talk to me or Stephen Bates is also very highly involved in this.
Somebody here. If there are no more questions, thanks to all the fellows for thought-provoking talks on a range of topics, and thanks to all for coming, and hope to see all of you after lunch. Thank you.